Assalamualaikum class and good afternoon. So we continue our lecture today in chapter 4, right? So in previous video that I share with you, so it say that in order to solve a circuit with the AC signal, it is a best practice if we convert our time domain into a frequency domain or phasor domain. So in that video, you already know how we convert our time domain into frequency domain, and also we know that every element we have a resistor, inductor, and capacitor. They have their own form of a phasor domain. So and then we know that instead of we are using our first deriving the differential equation and then transforming it into a phasor to solve V naught. So we can transform all the RLC component into a phasor form first. So then apply any laws, KCS law and other theorem to set up a phasor equation involving the value directly. So we know that V of t in a time domain, right? In the time domain can be present by V, capital V with the Vm's and the P, the phase angle, and then dV over dt can be represented by j omega V, and then if you have a integration part, you can represent with V divided by j omega, something like that. And then you already seen that for phasor relationship for circuit element, right? For resistor, we know that resistor usually is not being influenced by the AC circuit in a high frequency input, we can say like that. So therefore resistor will remain the same for the phasor domain, which is V equal to IR, and then we know that for resistor, the voltage and also the current are in same pace. And then for inductor, so we know that inductor voltage can be found using VL di over dt. And then from here we know that if you have a differentiation, right, so you can transform that formula into V equal to j omega Li. And then we know that in inductor, right, so the current are not the same pace with the voltage for inductor, which is we can see that voltage for inductor leads current by 90 degree. Alright, so and then last one we have a capacitor. So I equal to C dV over dt, right? For the capacitor, the current given is I equal to C dV over dt. And then if we convert using this one, right, so we can say that I equal to j omega C V. And then we also know that in capacitor, current and voltage also not in the same pace, but in capacitor the current will lead the voltage by 90 degree, right? So this is a special relationship for circuit element. So we have three elements, which is R, L and C. For the time domain, right, so V equal to Ri, and then for resistor, and then in the frequency domain it's still the same, but the terms that we use now, we are using usually in a frequency domain we are using a vol V and a capital R and I, so V equal to Ri, right? So for inductor, V equal to L di over dt. And then we know that by using the formula, okay, so V can be represented in a frequency domain by V equal to j omega Li. And then last one we have a capacitor, I equal to C dV over dt. We know that from here is actually I equal to J omega CV CI sorry CV sorry, right? So and then therefore you can write the value of V equal to I divided by J omega C, right? So this is the example. We go to the example. Let's say if you are given a voltage V of t equal to 6 cos 100t minus 30 degree. So is applied to a 50 microfarad capacitor. Calculate the current I of 3 through the capacitor. So we know that this is actually the circuit. Okay, the value of the capacitor is 50 microfarad, and then V of t here. Okay, I convert directly to the Passer form. So you got 6 with the degree of negative 30, with the phase angle of negative 30 degree, and then therefore in order to solve this, we know that we need to convert all the circuit into a Passer form. So this one I already converted into a Passer form. So next we need to convert your capacitor into a Passer form. So therefore we can say that XC is actually equal to 1 divided by J omega C, which is equal to 1 J. Omega value is given over here, so which is 100, right? And then C is actually equal to 50 micro. So by using your calculator, so therefore we can say that XC equal to negative J 200 ohm, right? So therefore you can calculate the value of I over here. So by using I equal to V divided by Z, which is V is 6 negative 30 degree, and then Z is actually negative J 200. Okay, so you can convert this one into a Passer form, into a polar form. Okay, let we do this by using your calculator. So right, by converting your negative J 200 into a polar form, so you got 200 with a negative 90 degree phase angle. So therefore just put in here. So by using your calculator, right, you got 30 milli with phase angle 60 degree. Alright, so therefore, if you convert this one into a time domain again, so we know that this is your phase value, this is your phase angle, so the capacitor will remain the same. So therefore, in a time domain, your current will be given as 30 cos 100t plus 60 degree milliampere. Okay, next we continue with impedance and admittance. So what is impedance? What is admittance? So Passer allow us to express current voltage relationship for inductor and capacitor, much like we express the current voltage relationship for a resistor. So a complex exponential is the mathematical tool needed to obtain this relationship, right? So the impedance Z of a circuit is the ratio of Passer voltage to the Passer current. So we know that Z is actually equal to ratio between your Passer voltage with the Passer current. So the unit for impedance is actually equal with the resistor, which is ohms, right? So the unit is ohm. Okay, so therefore, if you see here, impedance is actually ratio between the Passer voltage with the Passer current. So therefore, impedance also equal to R plus JX, which is R is actually your real impedance, usually consists of resistance, and then X is actually your imaginary impedance, which is a reactance. So when I say reactance, usually reactance refer to the either you can have XL or XC. So XL is actually reactance for inductor, and XC is actually reactant for the capacitor. So therefore, if you got a positive X, so that's mean your reactant is a inductor, right? So if let's say you have a negative X, so that's mean your reactant is actually a capacitor, or you can write like this one, R plus JXL. So usually when your reactant is inductor, so you got a positive over here. And then when your Z is R minus JXC, so usually when your reactant is capacitor, so usually it represented by a negative sign of you got a negative sign for the reactance, right? And then we also have admittance. Admittance is represented by Y. So admittance is similar with the conductance. So we know that in a DC analysis, you got R and then equal to 1 over G. So which is G is your conductance. And then for the AC circuit, so G is represented by the admittance or Y. So admittance Y is actually the reciprocal of impedance. So therefore, it's measured with the same value as conductance, which is Siemens. Right? So therefore, Y equal to 1 over Z, which is reciprocal to impedance. So therefore, Y is actually equal to I divided by V. Okay. So this is IV relationship and impedance of a resistor. So we know that, okay, we know that in this one, right, in this figure, we know that this basic resistor and inductor, current and inductor for the capacitor is only in space, right? So therefore, we can see from here, I of t and V of t reach the peak M simultaneously. So we can see that is in phase if your impedance equal to R, or is your impedance equal to the resistance value only. Okay, real. Right? So this is IV relationship and impedance for inductor. So let's say you're given this current for inductor, so and then we know that V of t equal to L di over dt, and we know that also in inductor the current will in inductor, yeah, the voltage will lead the current by 90 degree, right? So voltage leads the current by 90 degree. Therefore, in a phasor transformation, so you got V equal to L J omega I, which is J omega I here is your your current, right? So therefore, impedance for inductor is given by Z divided Z equal to V divided by I, or equal to J omega L, right? If you bring I over here, so therefore you got Z equal to J omega L, right? And then this is graph for the inductor, which is you can see here the voltage lead the current by 90 degree, right? So in this case we can see that impedance equal to J omega L, and is purely positive imaginary. So usually by saying this, actually Z equal to J omega L, we know that actually Z equal to can be R plus JXL, something like that. So but in this case you don't have R equal to 0, then we can see that your impedance is purely positive imaginary, right? And then for the capacitor, so this is your capacitor I of t equal to C d over dt, and then I equal to C J omega C. In the impedance, we know that is a ratio between your V and I. So by bringing your V and V divided by I over here, and then bring this one to the left, so you got Z for capacitor is equal to 1 over J omega C. Alright, so and then in capacitor we know that current is leading the voltage by 90 degree, or you also can say that voltage lags current by 90 degree, right? So in impedance, usually Z is equal to 1 over j omega c, and then we can say that usually the value of this impedance for the capacitor is purely negative imaginary. Alright. Alright, so impedance Z is a complex number in units ohm. So, and therefore, right, so this one, real impedance is usually consists only of resistance, and imaginary impedance X are called resistance and this one is called a resistance, right? And then the imaginary part usually called a reactance. So although impedance is a complex, it's not a passive. In other words, it cannot be transformed to a sinusoidal function into time domain, right? So you must know between complex form and also passive form, guys, right? Complex form, so that's mean you got this, you have this rectangular form, which is r plus jx for z, and then in order to convert this, you need to use a calculator, right? So you can convert this one into a polar form. We call it a polar form, we not call it a passive form, right? So which is you got z with certain value of r and z, and also the phase angle, right? So summary for impedance and admittance. So impedance and admittance of basic element R, L, and C. So impedance for resistance equal to R. Okay. Impedance for inductor is actually j omega L, and then impedance for the capacitor is 1 j omega C, and then admittance for the resistor is 1 over R, and then admittance for the inductor 1 over j omega L, and last one in admittance for the capacitor equal to j omega C, right? So this is already explained, right? I think this is already explained in the previous video. So we know that for a capacitor, inductor, so inductor always act like a short circuit in a DC, but in a high frequency, or we can say that in AC circuit, usually inductor is equal to open circuit at high frequency, right? And then for the capacitor, if let's say a capacitor in DC always represented by open circuit, right? And then for the high frequency or AC circuit, usually capacitor is represented by the short circuit over here. Alright,